I have the pleasure to introduce Bart Simons. Bart Simons is working in the Royal Military Academy, where he is a professor teaching general chemistry, but also, of course, forensics and on analytical methods of energetic materials. So this session for this afternoon will be how to deal with energetic materials. It's meant as being a general introduction, so covering a lot of topics on this energetic materials. Also, I think in the next week or the week thereafter, Bart will give also a session, but then more dealing with the analytics. So how to determine explosive and explosive residues in soil. So please, Bart, the floor is yours. And yeah, take once in a while a moment for questions, and then we will follow the chat. Good luck. Thank you.
Yes, thank you, Christophe. So well, welcome everybody. I will just have a quick look. 22, including myself, so 21, welcome, and thank you for being here. So I will indeed present the presentation with the title Dealing with Energetic Materials. Just as an introduction, who are we? So the Royal Military Academy is situated in Brussels, in Belgium, very close to the town center, actually. And I am actually weaving to you from this small window that is indicated on the slide. And so this is where my office is. This is where I am now. And this is the place that most of you will visit somewhere in November or in 2025. We are a military university. We prepare the future officers of the Belgian Armed Forces, and we have different departments as any university, and one of them is the Department of Chemistry, of which I am the head. And we are specialized in energetic materials. What do we do? I usually say we treat them from the birth until death. And then the birth is the synthesis, so we can synthesize different explosives and energetic materials. We have a lot of tools which are mentioned on the slide to do the chemical characterization, which is the typical analytical lab work. And then we have also very many tools to do the physical characterization. So you see some aspects here. I will come back to some of those during my talk. We talk about how good an explosive works, how sensitive it is, how does it age, is it changing a lot or not? We have a lot of equipment for that, and that equipment is always growing. And so we can do basically anything with energetic materials. And then the end of the life is after it has been used. We do the post-blast investigation for any incident that occurs on Belgian soil. So as soon as there's an intervention for a terrorist attack or a minor attack, then the EOD takes samples, and these samples are sent to our laboratory. So this is very short, who am I and who is our institution? And so I think it was a quite logical choice that we did the explosive part of the analysis in this project. This is the content lever of my talk. So this is 5 topics, some generalities, some basic things about energetic materials, a little bit about the chemical point of view, what do they from a molecular point of view, and then some properties. This is very general, as Christophe mentioned it in the beginning. So these are just some notions that I think are interesting if you are working with energetic materials, and also if you have to look for them in soil, it's good to know where they come from and why you find something and maybe not something else in a particular sample. And then 2 things that are more specific for this project is how do energetic materials get into the environment and what happens to them in the environment. I think this part might be quite similar to other talks that you have. So if I am repeating too much of what has been said before, don't hesitate to say, yeah, we already know that, and pass to the next slide. And then a final thing is about the toxicity of energetic materials, which is basically the problem, or the reason why we do what we do is because it's not so healthy to have them in the soil and then in the human body maybe. So these are the 5 topics. Let's begin with the beginning. generalities. And I heard from Christophe that there was a little bit of confusion about what is an energetic material, but it's actually a mixture of three types, three groups of compounds. And one of them is probably the most speaking, it's the explosives. I put a couple of pictures on the slide. We see up, if I find the cursor, we see a mine, we see a bomb in an airplane, we see mortar shells, artillery shells, at least the part that is indicated. They all contain explosives. So explosives are very, very common on a warfare terrain. A second group are the propellants. If we want to fire artillery shells, we need to propel them for 10 or 20 kilometers far away. Propellants are also found in small arms munitions, because bullets also have to be propelled, and then also in missiles, of course. And that's a second group of energetic materials that is also of interest for our project, because the D&T we have to look for might mainly come from propellants. And then there's a third category, which is less important in this project, but nevertheless, it is part of the energetic materials, and it's the pyrotechnics. In pyrotechnics, I automatically think of New Year or a birthday and a lot of light in the sky, but they are also used in a military context, for example, for illuminating munitions. And so these three types of energetic materials are part of that one group and are being found on or during warfare as Ukraine is suffering now. So that's the reason why I called it energetic materials, because it's a little bit more global than just explosives. If we look at the subgroup of explosives, I just put two definitions on the slide. You can read them for those that can read in English. But basically, any definition comes back with the same types of properties to be called an explosive. There's a chemical reaction. It's in pink here, and it decomposes, which is basically a type of a chemical reaction. In blue, we see speed and we see rapidly. So it has to be a very rapid process. And then that process, that decomposition, that reaction will produce gases in green and heat. And heat will, of course, increase the temperature of the gases. So any definition that you can find will contain the same information, more or less. Something happens to the molecules, they will decompose, they do it very rapidly, and they will produce hot gases. And these hot gases will have a lot of effect on the environment. So this is basically the summary of all this, a sudden, very rapid release of energy under the form of hot gases. Now, if we think of an explosion, there are certain things that always come back because of that sudden release of energy. It's typically the bang, a loud sound. If you don't protect your ears and you're too close, you can get deaf or partially deaf. There's a fireball which can hit you or hurt you, but it's usually in size quite limited. And there's, of course, a shockwave, and that's the part of the munition or the explosive, the explosion, that will cause most of the damage, because it can hit a structure, it can hit a tree, and the tree can fly and cause damage. It can break windows, and the window is shattered, and the fragments can hurt people. So the main cause of damage to people and material is basically the shockwave. If there is a casing around the explosive, as in all the examples that we saw of the mine and the shell and the bomb, then that casing is usually broken into fragments that fly at high velocity, sometimes big fragments. So they also cause a lot of damage and injuries or death to people. Now, if we think of sudden release of energy, then we can summarize it in more chemical definition, as we need chemical reactions that are highly exothermic. Exothermic meaning producing a lot of heat. And then a chemical reaction is always something that occurs between reactants, and the result of that reaction are products. And in this case, we call the reactants fuel and oxidizer. So one will be reduced if we look at it from a chemical point of view, the other will be oxidized in a redox reaction, and that will produce the products that are usually in a gaseous form. Now, the fuel and the oxidizer can be mixed in different ways. I call it a physical and a chemical mixture. A physical mixture is actually compounds, different compounds that I take from different jars, and I mix them together. And I usually try to mix them very well, so there's a good contact between all the components of the mixture, but it remains a physical mixture with grains of A and B that are in contact with each other. A second possibility to mix fuel and oxidizer is what I call a chemical mixture, where the fuel and the oxidizer are present within the same molecule. And that is, for example, the case for this molecule of TNT, where the fuel and the oxidizer are present within the same molecule. The advantage of that chemical mixture is that the distance between fuel and oxidizer is much smaller, which will allow a much more rapid reaction than for the physical mixture. And then linked to that, these two types of mixture, we have two different processes that we would consider as an explosion. And the first one is the slowest one. It's called a deflagration. A deflagration is basically a very rapid combustion. And that will typically happen if we have this kind of physical mixtures. The compounds are in close contact, but not as within the same molecule. So as there is a close contact, the reactant, fuel and oxidizer, can encounter each other rapidly, and the reaction can go quite with a relatively high rate of reaction. This is just a picture that shows the idea. At the right, we have the hot products, and then we have a reaction front that is advancing. The driving force behind that reaction front is the heat produced by the reaction. And the speed of this reaction front is smaller than the speed of sound. And that's typical for what we call deflagration reactions. That's typical for propellants, because we don't want them to explode and cause damage. We just want them to burn very rapidly. And if you would take a picture or a measurement rather of the pressure, if I take some point here in space and I look during the time, how does the pressure evolve, then we see that there's an increase. It's steep, but it's not sudden if we compare it to the next I will show. And then, of course, the pressure decreases back to the atmospheric level. Now, if we yes. The second, if we have the chemical mixture, it allows for reaction rates that are much higher. And we will have a reaction zone or a reaction front that moves at supersonic speeds. Now, supersonic is relative to the speed of sound of this unreacted explosive. If you want some numbers, a deflagration, this front is traveling at anything between 1 and, let's say, 1,000 meters per second. In a detonation, where this is supersonic, we can have speeds up to 8,000, 9,000 meters per second. So there's an order of magnitude difference in the speed of the reaction. And in this case, this is a shock wave traveling to the material. And instead of having my mouse is a little bit slow, so I'm having difficulties to indicate. Instead of being thermal, it's a shock wave that will induce the reaction. And because of that high speed, we see this typical pressure profile for a detonation with a very sudden increase from atmospheric pressure to peak pressure, while in this case of deflagration, the increase was steep, but not as immediate as it is for the detonation. And then, of course, we have the decrease of the pressure, which is usually exponential. So these processes are not to be confounded because they have very different effects on the environment. This is not so damaging as this is, for example. Just one thing I would like to add, if I click on the bottom, an explosive that can detonate will not always detonate. If I take a block of RDX, I can put it on fire, it will slowly burn. So it's not because something is an explosive that by definition it will detonate. It depends on what I give to it as a stimulus, as an impulse, and it depends on the impulse how it will react. So that means that you can just burn a block of TNT without having an explosion and a shock wave, for example. So that's something that is also important to know. Generalities, just some basic things. Are there any questions?
I'm looking at the chat, Bart, but at this moment, no questions appear. So I think you can proceed to the second point of view from a chemist.
Yes, okay then. Is the speed of my talking good enough? It's not too fast, because I sometimes have a tendency to speak a little bit fast when I'm having fun.
No, it's perfect to me. Otherwise, if the translators would have any issues, they can put it in the chat. But I think it's working, Bart, so it's fine.
Okay, yeah. Okay, perfect. Well, let's hope everyone is still awake. A chemical point of view. So we have a fuel and an oxidizer, we said. But let's look at what they look like chemically. This is the very nice name, explosive for any group that we can find in explosives. And we have a list of oxidizers, a list of fuels, and then some groups that can play both roles, and other groups that just lead to more energy that is liberated during the reaction. If you look at this table, we can just combine any fuel with any oxidizer, and that would give us something like more or less an infinite number of possibilities for explosives. However, there are not an unlimited number of explosives in use, and that is because there are a lot of constraints put on the material that we make. The first one, certainly as being part of the Belgian military, is the price. Budget is limited, so we want an explosive that is as cheap as possible. Nevertheless, it has to have certain properties. It has to be stable. If it's stored during a long time, it needs to be in the same condition after 10 years than it was after 1 year, because if we use it, and in Belgium, I'm not afraid to say that sometimes 50 years after purchase, we want to use the explosive, it has to be in the same state. Chemical compatibility, I put it to be complete, but there's not a lot of time to go into detail. But basically, if I mix different things, they have to, I have to make sure they don't react in an unexpected way. Sensitivity is a very important one. If I'm a technician at an airport and I need to hang a bomb on an airplane, I don't want the bomb to explode in my hands, of course. And someone who is putting the artillery munition in the artillery pieces doesn't want the same thing. On the other hand, we don't want the explosive to be too insensitive, because otherwise I can never get it to detonate. So it's kind of like a compromise. I want it to be a little bit sensitive, but not too much. And that excludes also a lot of the possible combinations between these fuels and oxidizers. Explosive output properties, basically the effect I want to create. Is it a large effect, a small effect, and some of the combinations I can invent will just not be performant explosives. And then an important one, I think, as well, is the toxicity of the compound I make. I cannot just combine anything, throw it somewhere if it's very polluting from a toxic point of view. So if we take all these factors into account, the number of combinations that we can make with these groups is quite limited. So in the next slide, I will just run through the most common ones, sometimes with a little bit of comment. And then it's not something to learn by heart, of course. It's just to give an overview of what exists. So this is an example of a molecule. It contains the fuel, it contains the oxidizer. TNB stands for trinitrobenzene. And it is a good explosive. It checks almost all the boxes. It has good performance, stability, sensitivity. The only problem is that it is very difficult to synthesize, because putting one nitro group on the benzene ring is quite easy, but then it becomes more difficult to put a second one, and it's even more complicated to have a third one. So this process is complicated, and a complicated process comes with a price, of course. So this was initially a good explosive, but it was too expensive to go into mass production. Fortunately, people found that if there's a methyl group present, the synthesis and the addition of the three nitro groups is a lot easier, and TNT was invented or discovered. At least the properties were decently discovered. And so TNT, trinitrotoluene, is one of the most famous compounds, is also one that we had to look for in this process, because still nowadays, although it's very old, it is still used quite a lot. Just to be complete, this is one isomer of TNT. Here you find other isomers. Inevitably, if I start from toluene and I start nitrating, these others will also be formed. And so during the synthesis process, if I only want to keep the 2,4,6 version, I will have to remove all these. Process becomes a little bit more complicated because apart from the isomers of TNT, also isomers of DNT will be formed in the process, because these are just TNTs that have not been fully nitrated. So these will also be present in the mixture after synthesis of TNT and will also have to be removed. Inevitably, there's always traces of the 2,4 and the 2,6 DNT left in TNT, but these are actually minor, and I don't believe we can find them as if TNT is the source. So DNT is the second molecule we had to look for in the analysis. I think there's a good reason to look for it, but the reason is not because it's a byproduct of the synthesis of TNT. But I will come back to what is the good reason then, of course. These are other nitro compounds. Picric acid is not really used anymore. I just put it for completeness. TATB is used in nuclear weapons. It's very expensive. Lead stiff nut, I put it on the slide because it contains lead. Lead is a heavy metal. It's to be avoided. So this is one of what I will call the primary explosive, but I will get back to that. That needs to be replaced, because it would mean that each time I fire a shot, for example, there's a little bit of lead that enters the environment, and nowadays that cannot be justified anymore. Tetril is something that you can also encounter as an explosive, but it's not as common as TNT or RDX. In the nitrate esters, and I'm sorry for this list, it's not really interesting, but we have to know which compounds we are talking about. Nitroglycerin is a very known one, I think. It's a liquid. It's very sensitive to impact. There have been a lot of accidents in the beginning of the manufacturing of nitroglycerin, and it is never used alone as such. It's always used in combination with something else. That something else is very often nitrocellulose, also on the slide. So the combination of nitrocellulose and nitroglycerin is a typical propellant powder. PETN is used quite a lot now. It's used as one of the compounds in Semtex. It's also used in detonation cords, so it's quite likely that you encounter it on the battlefield. And if I'm not mistaken, we found PETN in some of the samples that were sent to Belgium. I also put ETN on the slide. ETN is not something that is used in the military, but it's a compound that nowadays triggers a little bit of fear in the European security, because it's a homemade explosive. It's quite easy to make. It's quite sensitive, so it's a little bit dangerous to manipulate, but it has good detonation properties, and it is considered one of the possible next threats by terrorists. RDX, HMX, the two main representatives of the nitramines. RDX is the molecule, the third one we had to look for. And we also did a screening and found quite some samples that contain also HMX. So these are still the most, I would say, one of the most recent, mostly used explosives. So it's not really surprising to find them in the soil on a battlefield. Peroxides, just to be complete again, TATP, HMTD, the classic terrorist explosives, because they are, I always say, easy to make. You have to pay a lot of attention to your fingers and your eyes and the rest of your body, because they're very sensitive, but they're quite easy to make by anyone, and they are all around the world. They have been used quite a lot, certainly TATP in terrorist attacks. And then finally some inorganics. Basically, all the two left ones contain mercury, contain lead. These are primary explosives. Again, the problem that they contain these heavy metals that we want to avoid nowadays. Ammonium nitrate, it's basically a fertilizer. But I think most of us will still remember what happened in the port of Beirut a couple of years ago. There was a giant explosion because several tens of tons of ammonium nitrate were stored there. Something happened, an accident, and it detonated. So it's mainly a fertilizer. The farmers in the US have tons of it on their farm. But if you use it correctly, you can make it detonate. So it's actually also an explosive which is used a lot in civil. A little bit more fuel in the mixture. This is one to show that we know TNT, we know RDX. That's the most common explosives that we know and that are still used. But there's still a lot of research going on in the domain of the explosives. And two things are looked for: green, which is on the in a certain way contradiction. We try to kill each other with products that are good for the environment. That it has a little bit of a contradiction in it. And the insensitive munitions, in the sense that we want to reduce the number of accidents, but as I mentioned before, they cannot be too insensitive or it becomes something inert instead of an explosive. And so these are CL20, FOX7 are names that maybe within 10, 15, 20 years might be common explosives and to replace TNT and RDX or HMX. That was for the explosive gunpowders, and that is where it becomes interesting again for this project. Typically single, double, triple base powder. Single base only nitrocellulose. Double base we have nitroglycerine and nitrocellulose. And for the triple base we add a third compound, which is nitroguanidine. The reason to mix 1, 2, or 3, it will take us too far. It's a matter of regulating how much smoke is produced, how much flame is produced, how high does the temperature become. Important for us, one of the additives that is added to a single, usually single base powder to nitrocellulose is 2,4-DNT. And this is why it's a good idea to look for it in the soil, because as part of TNT, we will probably not find it. There's only a fraction of DNT in TNT. But as part of the propulsive single base powder, there can be quite a lot of DNT. It's used as a stabilizer or as a to lower the temperature. And there, that might be an important source of DNT into the environment. A small summary I took from an article. The reference is on the slide. One comment to make before talking about it. It's of course about Western weapons. So it doesn't take into account any Russian weapon, because I didn't find a lot of information about the explosive they contain, which in a sense is not so unlogical. What do we see? A lot of TNT, RDX, and DNT as a chemical of concern for the single base propellant. So the choice for DNT, TNT, and RDX as the main compounds to look for in the analysis, I think was very logical if you look at these Western weapons, of course. So I think this justifies the selection of these three compounds. Although I didn't do the selection myself, I think it was a very good choice. Explosives, of course, they have to react. So a little bit on the chemical reaction. If you want to see what are the products of an explosion, there are some basic rules. They are very simple to use. We teach them to some of our students who are in the less scientific faculty. And you just have to see how much oxygen is required for the carbon, for the hydrogen. Basically, very simple rules. And with these rules, we can predict how much heat will be produced by that chemical reaction. Of course, these basic rules, just having some difficulties with my cursor because it moves slower than my hand. These basic rules, they give a good estimation of the amount of heat that is being produced during the explosion. Now remember, an explosive had produce heat and hot gases very rapidly. We also have tools, complicated calculations and a computer to determine a more precise composition, and that will give us a more precise estimation of the heat of the detonation. Now, why do we need that heat? That's something that I will talk about in the next paragraph, which is a few words about properties of energetic materials. But maybe it's a good point to ask again if there are any questions in the audience. At least I'm sure I'm not talking to my computer.
No, 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 you're not talking to computer. And from my point of view, being a chemist, I found it very interesting to see indeed, Bart, the different structures that are being used. I don't see anything in the chat right now. Also, no raised hand, Bart. So
Okay.
you
I don't know
can.
if that's good, but
I think it's good.
I will just believe that. Okay, so the third one, it's the last one specifically about the general topic of energetic materials, are just some properties, things that we need to know about energetic materials when discussing them. And on this slide, I will explain two very different properties of one and the same explosive or different explosives. And the first topic, you can see it here, is power. Power is linked to the capacity to perform work, push something. Power is what we will want from a propulsive formulation. It must not break the bullet in small parts. It must not break the weapon into small parts. It must push a bullet as fast as it can go. And it has turned out from the theory, from experiment, that the heat of the detonation, the Q in the previous slide, and the volume of the gases that are produced, that the multiplication, the product of these two, is a good estimation for the value of that power. We see just some examples. We don't have to really see the values. We just see that some heats of detonations are higher than others. Same with the volume of gases. And in function of the power that I need, I must look for a compound that has a product of both that satisfies my needs. Now, if you look at the pictures, this is the initial situation. It's kind of like a cylinder with a screw on top. Power, if I have power as the property of my explosive, it will push against the walls. It will push against the top and the bottom, but nothing is broken except that the top has not resisted the pressure and the bottom neither. But the cylinder is still intact. It has just increased in volume because the hot gases have pushed against the wall, but the wall is not broken. That's power. That's what I want for propulsion. That's also what is used in quarries. If I have a marmor quarry and I want to break a piece of marmor off, I don't want all tiny particles of marmor. I want a big chunk of marmor. So I will push it away from the rest of the marmor by using power. And the opposite, in a certain way, is brisance. Brisance is the scattering effect of an explosive. This is the same initial situation, this cylinder with a screw on top. This is the result if I have a high brisance. It will tear everything apart in small pieces. This is what I want from an explosive in a hand grenade, in an artillery shell, in a mortar shell, in an airplane bomb, because the casing of that bomb or shell has to be teared apart in small fragments that fly away and hurt people or structures or vehicles. Now, it's not the heat and the volume of gases that are involved here. The main parameters are the velocity of detonation, the rate at which the detonation front is advancing, and as I said, it's several thousands of meters per second, and the density is also playing a role. And then if I want a high brisance, if I want to break something apart, I will look for the highest VOD at the highest density. And if I look for power, if I don't want to break things, but I want to push them, then I will go for a high heat of detonation and a high volume of gases. So basically what I take as an energetic material depends on what I want to do with it. That's mainly the message of this slide. And so the notion of brisance and power is something that I think is interesting to understand and to know about. Sensitivity is a very important one because sensitivity is linked to safety. There's sensitivity to impact. For example, if I drop a piece of explosive, what is the probability that it will explode? Friction, it's just friction, as the word says it. For example, if I have a piece of explosive in a rocket, and that rocket accelerates from 0 to its maximum speed, there can be friction on the inside of that rocket between the wall of the rocket and the explosive. So that sensitivity is important. Electrostatic discharge, it's less of a problem in practice. Shock, if I have a compound with different munitions, if one munition detonates, how probable is it that the one beside it will also detonate? That's a shock wave traveling from one to the other. I want to know how sensitive is the second one to that initial shock wave. And so these sensitivities are very important parameters in an explosive. Something that is too sensitive to manipulate, and it cannot be used for practical purposes. Now, I've just put some examples for friction and impact on the slide. Here are the three main compounds we are playing with in this project, and we see for friction they are quite insensitive. You can basically not have an accident because of friction. Impact is the same thing. You can drop them; they will not detonate spontaneously. So this makes them secondary explosives. Secondary explosives are explosives that require a quite high stimulus to get to detonation. And it is opposite to what is called primary explosives. If we look at the numbers here, we see that at least for one and maybe for several impulses, they are quite sensitive. The lower the value, the more sensitive the compound is. And we see that TATP, which is used by terrorists, they carry a backpack full of it or a transportation bag. This is very dangerous to handle because the smallest impact or the smallest friction can cause an accident. Others here, like the ones we saw in the overview of the different molecules, they are also quite sensitive to friction, and that allows them to be used as primary explosives. Primary explosives can get to detonation with a much smaller impulse, which leads us to the idea of what is called between I don't know the name of the symbol in English, the explosive train. An explosive train is a succession of different compounds, each one being less sensitive than the next one. And that explosive train always begins with a primary explosive. The primary explosive is very sensitive. That's something you don't want to touch with your hand. That's something that you have to be very careful with. And usually that's what we call the detonator, the part that contains the primary explosive. Usually this is followed by a booster. The booster is a secondary explosive which will detonate because of the shock wave induced by this primary explosive. And then sometimes there's a main charge, which is the basic charge, the largest mass, that is the least sensitive, that requires the shock wave from the booster in order to detonate. Now, why do I talk about this? Because Nathan Park asked me a little bit about UXOs and what to do with them. And this type of explosive train is also what we find in any munition. So this is the example of artillery shells. In the body, we have the main charge, the explosive, with a lot of brisance to scatter this shell into small fragments. But on top, the blinking part is the fuse. And in the fuse, we have primary explosive. That is very sensitive. That is supposed to detonate on impact or proximity, depends a little bit on the type of fuse. Now, why do I talk about this? Because of the topic of UXO. UXO stands for unexploded ordnance. Some munition has been fired. The intention was that it would explode, that it would act as it was intended to do, but it didn't. and it remains unexploded somewhere on a battlefield in a city, and the different examples that we see. So one of the questions was, yeah, can you talk a little bit about UXOs, markings? Honestly, markings, it's way too complicated, and certainly Russian Western one is different. So I cannot talk about that. But one of the questions in the mail was also how to deal with it. So I asked that question to I have to switch my pointer off. How can I not have a pointer anymore? Highlighter, no. Christophe, can you maybe tell me how to switch everything off? Okay, yes.
Yeah, you find it?
Yes,
Okay.
but otherwise I cannot click on the link. So I asked my EOD colleague dealing with UXOs, what can we tell? And his message was very short. If you encounter a UXO somewhere, something that didn't explode, first rule, do not touch it because of that explosive train and the fuse that might be switched on but didn't function. Maybe just the slightest touch might put it into action and kill you. Second thing is mark the location so that no one else stumbles upon it or touches this by accident, and then report it. In the military, of course, it's to the military chief, but in a civilian environment, it's maybe to the police or to a military commander or to some soldiers passing by, I don't know. But these are the basic rules. Don't touch it, make sure no one else touches it, and report it to someone that they can call a specialist. And so here you see the marking that has been done. In other cases, can you see my cursor of my mouse?
Yes, we can see it.
Ah, it's easier than the laser. And in this case, the reporting has been done, and specialists come on site. They know to identify, they know how the system works, they can verify is the fuse still dangerous or not, how to remove it, how can we safely defuse it, and they know what to deal with it. But don't touch it yourself, don't try to move it because it's on a road, it's in your way on a field or whatever, it might just cause a sad accident. That was a few words about UXOs, about that explosive train with the primary. And the big problem here is not the secondary explosive, the main charge that will not detonate spontaneously. It's always the fuse that is the most sensitive part and the thing that you have to be careful of. And one last notion that I would like to talk about is TNT equivalence. It's a very famous thing I think about explosive, and it's a very controversial thing in my opinion. Context, all explosives are different, meaning that they have different properties. They create a different pressure, a different heat, a different volume of gases. They have a different velocity of detonation, a different brisance and power and whatever. So if you want to write a regulation, be it for legislation or be it for safety distances or whatever, it's difficult to write a text that is convenient for every explosive separately. You cannot write a text for TNT and one for RDX and one for every explosive. So basically the idea was we take one explosive as a reference and we compare all the other explosives to that reference. And so we write our legislation or our safety procedure for the reference explosive. And with that notion of TNT equivalent, we can translate a mass of any explosive into a mass of our reference explosive. And the reference that was selected was TNT. So if we look at the table, it's just some examples. If we want to know what this means, if I take RDX and I have some safety issue that is about power, so I work with the heat of detonation, we see a number of 1.39 in this table. That means that 1 kilogram of RDX will have the same effect as 1.4 kilograms of TNT. And if my legislation says you can shoot 1 kilogram of TNT, then I cannot shoot 1 kilogram of RDX, but I have to divide by this factor. So this notion of TNT equivalent allows me to calculate a mass of any explosive, transform it into a mass of TNT, and then I have all the documents about TNT that allow me to calculate safety distances or a maximum amount that can be fired on a shooting range, or the maximum amount that can be stored in a certain bunker. It's always a TNT equivalent mass that is used. The idea is good and it's practical, but as you can see, for one and the same explosive, I can find different numbers. I just put 2 columns here, but I could have added a third and a fourth. Depending on the property that I compare to TNT, the value will change. And so it's sometimes difficult to say, yes, but I have 1 kilogram of RDX. Do I have to multiply by 1.4 or by 1.6? So that notion of TNT equivalent is practical in one way, but is a little bit confusing in the other way as well. That's the reason why I wanted to talk a little bit about it. Now, what do we notice as well in this table, that although the numbers are different, generally, if it's less than 1 for one property, it's also less than 1 for the other property. If it's more than 1 for one property, if it's stronger than TNT, it's also stronger for other properties that we compare. Voila, this ends my third part, the properties. If I look at my watch, maybe Christoph?
Yeah.
Maybe for 25, 30 minutes left.
Yeah. I just first had a question, Bart, with the example you give of this metallic recipient. You were talking about
Okay, yes.
the brisance and power, and in that table, I noticed for RDX that, I mean, it gives on both one of the highest values. So I was wondering, the one is more related to using at the propeller, the other one more for the fragmenting. Um, what makes then the difference? Is then the concentration of these products, or how do you deal to use it on the one, because you can use it then as a propeller, but if I understood well, also for fragmentation. How is this done?
By avoiding that it detonates. So if you get it to detonate, you will have the brisance effect. If you can make it
Okay.
burn without, so you don't give it a shock as an initiator, but just a flame, then it will quickly burn, and then you
Okay.
have
Okay.
more like the propelling effect.
Yeah. But this means that the product like RDX can be used as a propeller or as an explosive, if I'm right.
Theoretically, yes, but
Yeah.
as a propellant, there are better things. So in
Yeah.
practice, you will
Yeah.
not do it. But in
No.
theory, it is certainly possible. Yes.
Yeah. Okay. No, thank you for making that clear. Indeed, I think you were suggesting of having a 5 to 10 minutes break, so to visit the toilet
Well,
room,
it
have a
depends
coffee.
on the needs. Huh?
Yeah, but I
It
think it's
depends
fine.
on the needs of.
Just a 5 minute break, I would propose, and then let's continue within 5 minutes, I would suppose, Bart. Then, and
Yes,
I don't see
perfect.
any other questions, so we see each other within 5 minutes, I would say. Okay.
Okay, see you.
Ці лекції на сьогодні ще будуть сьогодні. Ну, писали собі якісь, мало бути, 14 до 1,5 години. Ну, це з 15 до пів 5 буде. І ще 40 хвилин буде.
All right. We had our 5 minutes break. So after your short course on the energetic materials, I think we move on now to the environment and other aspects. So please, Bart, proceed with the rest of your presentation.
Yeah, so thank you. Just one thing. Everything before this part was, let's say, common knowledge for me. Everything behind this is something that I had to study a little bit as well, because we are less concerned with the environment as the military than we should be, probably. So, and another thing is, as I said in the beginning, if I repeat too many things that others have told as well, we did not really fine tune our presentations to not overlap or to overlap. So if I repeat too much things, just stop me from what I'm doing. So first, a couple of slides of sources of energetic materials and into, or how they enter into the environment. The first one is probably the most important one from quantity point of view, but probably one of the less important if you see how many of these installations exist. And it's basically the places where explosives are synthesized or where they are used to fill munitions. And because there are such a large quantities of explosives on these sites, there's a lot of wastewater containing explosive or energetic material molecules. There's also dust of the explosive in the air or in the atmosphere. So these are the main places for high pollution in the soil, in the water, and also in the atmosphere. Now, the number of these locations is limited, so I'm not sure that's the biggest concern, but I think it's quite logical that around the factory you will find a lot of pollution of the stuff that is being used in that factory. I think the most important one for this case of Ukraine is munition that is being used as it is supposed to be used. And that's what I call on the slide the intended action of the munition. So as we saw, a lot of gases are created. That's a good thing because they just disappear. There's some CO2, but I think we produce more CO2 with our industrial activities than with our warfare. And then I put between brackets that there's maybe a small reminder of explosives. That depends basically on the quality of the detonation. If we have what is called a high order, a very good detonation, then literature agrees that basically everything is gone. But if you have a failure in the detonation for some reason, which we call a low order detonation, then there might be some explosive that remains even when a shell has detonated. There are fragments being formed, usually for most of the types of munition. These fragments, after flying away, of course, they fall on the ground. They might contain a little bit of explosive as well. And then bullet shells, they might contain a little bit of powder that has not burned. Apart from the aspect of heavy metals, I'm not really concerned about heavy metals. That is another topic. It's of course a big problem for the environment, but it's not really linked to the energetic materials as such. Now I will click on the link. We switch to the end of the presentation. A picture of a rocket launcher. If we see this picture, I think it's quite logical. Now we see a big flame at the behind the shooter, a little flame here. So it's quite logical if we want to look for energetic materials that it's mostly behind the rocket launcher that we will find propellants on the ground. Unburned propellants that have left the tube and that have fallen on the ground. There's also have been studies that show that in front there's also but much lower quantities of propellants. And then that rocket flies, of course, it follows its trajectory and it hits a target. In this case, it's a hit. What can we find at the location of the hit? Well, first of all, propellant that had not yet burned, because these missiles are made for a certain maximum range. But if you hit the target before that maximum range, but not all the propellant has burned yet, so it's quite likely that near the target some of the propellant will be found again, unless it has burned when the explosive detonated, but usually apparently that's not the case. In some cases the rocket just flies against the target, it breaks, it doesn't detonate, and then we don't have this kind of situation, of course. And if the detonation is not complete, we might find some explosive. So these are locations where it's quite logical in a certain way to find propellants. And if you start sampling the soil, you shouldn't be surprised if you find nitrocellulose, nitroglycerine. That was the compound of concern, the DNT. And these are the locations where we might expect to find DAT in the soil. Artillery and small arms, they usually produce the flame at the end of the cannon, of the barrel. So where will you find propellant residue of the propagol? But it's mainly in front of these arms. For an artillery piece, it can be tens of meters in front. Of course, if you have a small gun, it will not be 100 meters in front of the gun, but maybe 1 or 2 meters. And then that artillery shell is flying, it falls on the ground. If everything works as it is supposed to work, it will create a crater in the ground normally. Nathan showed a picture of a lot of craters on a piece of ground in Ukraine. So that's the effect of a lot of artillery munition. And in that crater, we can expect to find some explosive. If we have to find it anywhere, it's probably in or very close to the crater that we might find it. So these are the sources of energetic materials in the environment if everything is working as it is supposed to work, which is of course a good dream, but not reality. So what do we encounter by the unexploded ordnance and the UXO, as we already showed? The problem with UXO is that they have been fired. So in a certain way, the system has been triggered and is ready to do what it should have done, but it didn't do. That's what makes it so very dangerous. What can we have in the UXO? Well, we have the material from the casing. If you leave a UXO for a long time in the environment, it will start corroding, and then the metal will disappear into the environment. If there's a lot of corrosion, but also if the casing broke after being shot, if the explosives come naked and there's no protection anymore from the casing, then they will start leaching into the environment, in the soil and through the soil in the water below the UXO. And then they will start degrading, as we will see, and we will also find degrading products. This is also an important source of pollution. If you don't clean the UXO very locally, you can have a very polluted soil. Depends a little bit on if the casing is broken or not, but it can be a location with a high concentration of explosive in the soil. An final type, I would say, is the ERW, the explosive remnants of war. It's basically munition that has not been fired. That's the only difference that separates it from a UXO. A UXO has been fired but didn't function normally, and an explosive remnant of war had just not been fired. There was too much munition, and you had to withdraw suddenly, for example. So you had to leave munition behind, or you had too much munition and you want to advance, you just bury it in the ground. That munition is usually a little bit less dangerous because it has not been fired. It is not, the fuse has not been switched on, and so basically it's not as dangerous to handle. Now, you cannot know if you encounter something on the ground if it has been fired or not in some cases. So I would just follow the basic rules: do not touch it, mark it, and report it, of course. And in the sense that it has not been fired, but it's similar to the UXO, but the pollution is the same as well. I think the probability that the UXO has explosives in the environment is larger because these munitions, they are usually intact, they are not broken, and the explosive is confined within the shell itself. And then the last one, I say maybe too much that they are important, but this one can be interesting as well, because all these things, UXO and ERW, they have to be destroyed at some point. You can clean an environment, you can store them somewhere, but at some point you have to get rid of that danger that is the UXO or the abandoned munition. And then you have to dispose of that munition, usually a task of EOD. And they have different options. If there's propellant, usually they will. It's becoming difficult in our country and in Europe. But I guess that if you have a lot of place and you are in a hurry, like in a warfare situation, there's the open burning where you just take your propellant, and as the word says it, you just burn it. It produces a lot of gases that are polluting the atmosphere in the environment, of course. What is usually done if it's not propellant but explosive, that is that they will take some munitions, abandoned or UXOs, they put donor charges around it, which means good, decent explosive where they are sure it will detonate, and that's the shells that has to be destroyed. They detonate the donor charge and everything is burned at the same time, and you have a non-military piece of metal after that procedure. But that releases a lot of explosives at the location where that disposal is being done. So the advantage of this is that you know where you do it. You can mark a zone, you can use a zone and say, don't plant anything for agriculture in this zone because we use it for disposal of munition. Nevertheless, it's part of the soil that is unusable for a certain time. And so this pollution is soil, air, and water. It's because of the gases in the open burn. So this is the once the molecules are in the environment, well, a lot of things can happen. On this slide, I put the processes that are linked to the molecules without changing them. If I talk about TNT, in all these processes on this slide, the molecule of TNT remains that same molecule with the benzene and the methyl and the 3 nitro groups on it. So that's why I call it remain as is, that there's no modification of the molecule. What can happen? It can adsorb into the soil, on the particles of soil. And once it has been adsorbed, then there's rain coming. I didn't take a picture of the rain, but it can leach into the groundwater. Leaching is getting into the water as the molecule such. It can be taken up by plants or animals. That's what we call bioaccumulation. And in some cases, it can also enter the atmosphere by a process called volatilization. These possibilities exist for the molecule as such. And then we have other possibilities that modify the molecule. So a number of processes have been added on the slide. All these processes will transform a TNT molecule into a different molecule. That's not necessarily a good thing because the new decomposition products can maybe be more toxic or more mobile or whatever. It becomes very complicated. But these processes will transform a TNT molecule into something else. What are these processes? Well, the first two, photolysis and hydrolysis, are two processes that don't rely on any life form. We call them abiotic. Photolysis is a decomposition under light. Photon is a particle of light, if you want. And hydrolysis is, of course, under the influence of water. Doesn't require anything except light or water. The biotic processes require some kind of a life form, can be a bacteria or a fungi or microbes, as you can read on the slide. And they will also transform molecules into other molecules, where hopefully the other new molecules are less toxic or less polluting. And then this is where it becomes very complicated, because what happens to that molecule in these biotransformations depends on so many different parameters. pH, what you learn to measure in this project. Is there oxygen or not? Do we have an aerobe or an anaerobe process? The temperature always has an influence on the rate of the processes. What is present in the soil? What type of soil is it? Are there metals that can act as a catalyst in the processes? So it becomes really difficult to give an overview. I will just state some general things that are important for the project, I think. So this is a very general list. I will go into detail on some of them, because some of these processes are linked to numerical values. And if we have some kind of a limit, and below that limit it is dangerous, then we can compare that limit to the specific numerical value of an energetic material. And so the first thing is volatilization. So this is the process where molecules enter the air, enter the atmosphere. There are two possibilities. Either the molecules, and I represented them here as orange circles, they enter the atmosphere after having been dissolved in water. And that is one first process that can happen. The mathematical equation that is behind this process is named Henry's law. And it gives a relationship between the partial pressure of these orange molecules in the concentration of these molecules in water. Now, this concentration of molecules in water depends on the molecule. Some molecules can have very high concentration in water, and other molecules have a very low maximum concentration in water. And that maximum concentration is indicated by the term solubility. Solubility gives an idea of how many of these molecules can we dissolve in a solvent, and in this case, the solvent is water. Now, what does Henry's law say? That if I have a certain concentration in my water, the pressure of these orange molecules above that solution is proportional to that concentration, and that proportionality is expressed as Henry's law's constant. And this is a numerical value that you can find for a lot of compounds, not only energetic materials, but all of them. Maybe you already saw some values in the previous presentations, I don't know. Now, somewhere, and I can give the reference to the interested people, someone put a limit on the value of Henry's law constant. And he stated, the author of the article stated, if you are higher than this value, then you might have to think about volatilization from water. If your Henry's law constant is below this value, then you must not worry about volatilization. So we keep in mind for this time the 10 minus 5 and the units, it's atmosphere, it's cubic meters, and it's per mole. So that 10 minus 5, I will not just spoil everything, but that's the limit we have to take into account for our energetic materials if we want to know if volatilization is going to be a problem. In other words, will there be molecules in the gaseous phase that we can inspire and that can make us sick, for example? A second possibility for volatilization is not from a solution, but from the compound itself. If I have a UXO and the casing is broken and the explosive is just naked lying there, the molecule can just sublimate into the atmosphere. And so there we have the notion of vapor pressure. Vapor pressure will be the partial pressure of these explosive gas molecules, vapor molecules in the atmosphere when they are in equilibrium with the solid phase here. Now, this vapor pressure is what it is. It is a pressure. It is expressed in units of pressure, and it gives an idea of how volatile a substance is. The more volatile a substance is, the higher its vapor pressure will be. Now, we are quite lucky. Most of the explosives are relatively non-volatile. And so this is something we will not have to worry about as well. But I will just show you some vapor pressures for the compounds we are looking for in this project. So you can judge for yourself. It's really very low pressure. Bioaccumulation, yeah, it's the storage of molecules in a plant or in an animal or in a human, for example. And from what I understood from literature, it's there's one value. It's again a numerical value that you can determine experimentally that gives an idea of how good a molecule will bioaccumulate or not. And that is the KOW. It's the octanol water partition coefficient with a nice name. Basically, the principle is a molecule is more or less polar. Polar molecules have a permanent dipole and non-polar molecules don't have it. Octanol is a non-polar solvent. Water is a polar solvent. And so there's a basic rule that like dissolves like, meaning that polar molecules will dissolve very well in polar solvents and non-polar molecules will not dissolve in a polar solvent, and vice versa. So basically, the experiment is relatively simple. I take a little bit of blue water, and this time I have green octanol. It's a little bit exotic. And I just put some of my compound of interest. I shake and I analyze the water and I analyze the octanol. If I have a non-polar molecule, most of it will appear in the non-polar octanol, and maybe a little bit will remain in the water. Now, why is this interesting? Because if we talk about bioaccumulation, we talk about storing molecules in our body, for example, or in the body of an animal. And most of the things are stored in our fatty tissue, in the lipids. Lipids are non-polar. So basically, this test is used as an indication for how hydrophobic or hydrophilic is a molecule, how easily, how much does it, I will rephrase it, how much does it prefer a non-polar substance over a polar one? The higher the value, the more affinity for non-polar substances, the more likely our non-polar fat cells will store it. So this is the value that is used to judge the bioaccumulation of a compound. Now, it depends a little bit on what you want to read. What is the limit for danger? I put 3 references on the slide. They talk about bioaccumulation, and they all have a different limit below or above which they say it's possible bioaccumulation or it's not really a risk. And the Stockholm Convention takes 5. And then we have a European regulation that uses 4.5, and the JRC, so it's a Joint Research Center of the European Commission, they use a value of 3. Now, whatever value we take the lowest one. So we had the Henry's law constant of 10⁻⁵ that we had to remember as a limit. And for KOW, we will remember 3, which is the lowest limit. And just to spoil a little bit, we will see that all the energetic compounds that we are studying in this project are below 3. So we can have a first idea that bioaccumulation will not be a big issue for these compounds. And then there's another one. Oh, yeah, I may be going past my time here because I talk a little bit too much. And there's another one, that's the KOC. We had KOW on the previous slide. This is KOC. It is a little bit similar and it is a little bit dissimilar in the sense that instead of comparing octanol and water, I will compare soil and water. The principle is the same. I will wait for an equilibrium, and I will see that some molecules prefer water more than the soil. Now, soil is a little bit comparable to octanol in the sense that it is the non-polar part, and water is polar. And this gives again an idea of how likely it will be that my substance will remain in the soil or it will go into the water. That's a little bit the idea. So it's no surprise that you can determine KOC from KOW, for example. Although it's better to do a separate experiment. There's a link between both because they are more or less about the same thing. Now, I put a table on the slide. It's for pesticides, but I guess we can use the same methodology for explosives and energetic materials. That depending on the value of the logarithm of that value KOC, we will have highly or immobile and everything for low values, because most of the molecules will be in the water and water can transport them anywhere in the environment. Immobile, because these will mostly be fixed on the soil. They will stay on locally on site and they will not travel far away. The rate of that mobility depends on a lot of things. The explosive polarity and the shape of it and the soil and the organic matter and you can read it for yourself. There's a lot of parameters playing a role, but as a first estimation, this table gives an idea of how likely, if I have pollution at some site, how likely is it that the pollution will go far away from that site or not. There are other things that play a role. TNT has a good affinity for soil, a higher affinity than RDX, but that affinity is reversible, while RDX, once it is linked to the soil, it will not be removed from it anymore. So it's more complicated than that, but as a basic rule, we can use this table, where we will see that we will mainly play in the domain between mobile and moderately mobile. Okay, having said this theory, apply it to our molecules of explosives. So TNT is the first of the 3 that we had to look at. So what is the probability that it will remain as is? But it's quite small because there's a lot of things happening to TNT in the soil. The only reason why we will find TNT is because there's a large chunk, for example, and it takes a lot of time to erode and to be removed by water and then enter the soil. But if we have traces of explosive, usually they will relatively quickly disappear. Action with the light, photolysis, is one of the principal processes if it's surface water. So water in contact with the light, that's one of the main processes that will decompose TNT, and it will turn it into TNB, and the trinitrobenzene. And then there's a lot of things going on in the soil, in water. I have this link. This is actually interesting, I think, in the sense that it depends a little bit on the point of view if it's good news or if it's bad news. This is an article about forensics. And forensic scientists, they want to find traces. So basically, the reason behind this study, where we see that the TNT degrades more rapidly if I store my sample at room temperature than if I store it in the fridge or in the fridge or in the freezer. Now, for a forensic scientist, if I want evidence that there was TNT, I will try to keep it in my soil, to have that evidence and to find it back. But if I'm looking at my soil from a point of view, I want to use it again, then I will try to keep my soil at room temperature, because there are processes going on that turns the TNT into something else. So it kind of cleans the soil. So depending on the point of view, it's good or bad news that the TNT degrades. And then I have some examples. It's not interesting as such, but just to show that there are a lot of bacteria that have been identified that are capable of degrading, of decomposing TNT. And there are fungal strains as well, more than one, that have been identified. And we have been doing a project on some munition that has been dumped in the sea. And there was a group as well that identified a series of bacteria that were able to consume TNT. So this is something that has been studied quite extensively, and most of the TNT will just be transformed into other things, which is good because the TNT is gone, which is not so good because these amino nitro compounds are not always less toxic. For bioaccumulation, what had we said? We have to look at the value of KOW. 1.6 is below the lowest, and the 3 of the Joint Research Center. So basically the risk for bioaccumulation is limited. There has been some observations that plants can take some TNT up, but that's not something to worry about, I think. For mobility, we had the KOC. We have 2.5 as a value, which would classify it as moderately mobile. That was according to the basic rule. So it will travel a little bit with water, but it's also stuck in the soil. It's somewhere in between. And then we have the volatilization. But if we look at Henry's law's constant, we had our value of 10 minus 5. We are below that value. So according to that rule, we should not worry about it. Now, just for the fun, because that's what I like in life, I made a little calculation. So if we look at the maximum solubility and the maximum amount that we can have is so much milligrams of TNT per liter of water. I can transform it into mole and to cubic meters and multiply it by this constant. And this is the partial pressure that I would have. So this is the concentration maximum that I would have of TNT in the atmosphere. This is based on the vapor pressure. So basically these concentrations are quite low and we should not worry about it. RDX, same type of slide. The processes are slightly different. RDX is not as easily turned into decomposition product as TNT. So it's more likely that we find RDX as RDX molecules than it is that we find TNT. We have the same processes that go on. We have photolysis with formation of the nitrosamines. So this is the NOO bond. These are potentially cancer. It is a very difficult word, but they might cause cancer. So this is not necessarily good news that RDX is transformed into this. And then I also have an example here of different microorganisms that can transform RDX into other compounds. So it's basically a little bit story similar to TNT. We have processes in water and soil that would lead us way too far, and it's absolutely not my specialty. Hydrolysis, not in natural water, but if the pH is high enough, we can observe it. If you look at bioaccumulation, 0.87, it's even smaller than for TNT. So we should not worry too much about bioaccumulation. There is a very interesting article of someone who spiked the soil and then planted different crops on it, like tomatoes and radish and lettuce. And that study actually concluded that in the edible parts of the plants, there was RDX that was detectable. Now, the concentration they put in the soil was rather high and much higher than the values we found. But nevertheless, that value of KOW is not so high, but bioaccumulation in plants have been observed. And if a human eats the plants, of course, it's bioaccumulation in persons, of course. For a mobility, we have 1.8, it's below 2, so it's what would be classified as mobile. And then I just have an interesting study, the reference is here, where basically they spike a soil and they try to determine the breakthrough curves. So there's water that flows through the soil, and then they also measure the RDX that passes through the soil. Now, the details, it leads us way too far. But what we see is that basically there's a small delay, but RDX just travels through the soil and we detect it after a certain time. RDX for TNT on the right side, we see that the delay is much longer. So it's much longer retained in the soil. And moreover, the quantity detected is only 40% of what was injected in the soil, meaning that 60% of it stays in the soil, which explains that it's less mobile than RDX. This kind of studies kind of demonstrate that effect. So mobility is much higher for RDX than for TNT, meaning that if you have a pollution site, well, around that site, there's a higher probability that you will find RDX. Same kind of calculations for volatilization. Concentrations are even lower. And according to our friend, we should not even worry about volatilization from the solution because this value is lower than the 10-5. And then to end with DNT, well, okay, it's a compound that is not so dissimilar from TNT. Same kind of conclusions that we can draw. It's also consumed in different conditions with or without oxygen by different organisms. Bioaccumulation, mobility values are not so different from TNT, so the properties are quite similar as well. And if you look at these values, they are also quite similar to those of TNT. So not something to really worry about in my humble opinion. And then I have one topic left. I will try to not spend too much time on it, but I see there's one thing in the chat.
Yeah, indeed, Bart. Thank you for pointing out this environmental section. Indeed, the question is, what is the maximum permission level of explosives for soil, for example, sediments and water? And is there any regulatory document in Europe related to this?
Excellent question. I prepared a slide for that in the next section. So the answer will be coming.
Okay, and then maybe another question, Bart. Just for my knowledge, this material you're talking about, RDX TNT, under normal, let's say, atmospheric temperature conditions, these are, I suppose, like solids, crystals, or could you tell something about the physical appearance? Yeah, okay. So because at some point I saw you said if you have an unexplosive thing that's open, basically you must imagine that these are like solid kind of crystal materials that could sublimate, but you showed that it's not the case. But is this the physical appearance of these materials, or how do they look like?
Yes, TNT is usually yellowish, but TNT is yellow by itself, but it's mostly not pure. So, but that's a yellow solid that takes the shape. Usually they pour it, so they melt it because it can easily be melted, and the melting temperature is way below the ignition temperature. So anyone can just put it in the oven around 80 degrees, it melts, I think. And then you can pour it into a shape and it will become a solid. So you can make Christmas balls filled with TNT, or kind of like ochre color, dark green. RDX, if you look at it pure, but you will never use it pure, it's white crystals. It's similar to sugar. Am I still online?
Yeah, but you fell away for 3 seconds.
Yes, I had the notion, my computer said the internet connection was unstable.
Yeah.
So
you were just
TNT
telling
yellowish.
something about RDX. You were just wanted to tell about RDX.
And RDX is white. It's a bit like sugar or flour, depends on how fine the crystals are. But that is never used alone. It's always mixed with a plasticizer, and we usually use it in Belgium and Europe as C4, which is like plasticine, the Play-Doh, the toy, and usually it's white, but nothing prevents you from adding a color, of course.
Yeah. Okay. Thank you.
That's a very good question. I should have put a picture. That's something I didn't cross my mind. Sorry.
No problem. Okay, I don't see another question, so please proceed with the toxicity section, Bart.
Yeah, it's not so very long anymore. So that's also something everyone knows. How do we get? How can they act on us? But we have to get them into our body some way or another. And so you see the typical ways of ingestion, skin absorption, and inhalation. Ingestion can come from plants or animals that we eat, like the tomatoes that were grown in the study. If we eat them, we get some RDX in our body. And also directly, this is maybe funny, but just for the story, in Vietnam, the American soldiers had RDX. They can burn it. They used it to cook food, to heat food. And so sometimes it was on their fingers. They use their fingers to eat food, and they eat a little bit of RDX, doing it that way. And they even swallowed RDX as such because it adds to the effects of alcohol. So they just wanted to get drunk faster. So the ingestion is sometimes voluntarily done as well, but it can happen with water that we drink that is contaminated or whatever. Skin absorption occurs. It has been observed by people who work in munition filling factories, but it is relatively easy to avoid by putting gloves, as I put a picture on or by protecting your skin elsewhere as well. You don't do it in short sleeves, but you have long sleeves, etc. So this can be avoided. Inhalation, I think we have a lot of tools since COVID to avoid inhalation of substances. We have a lot of masks to protect us. So this is generally not really the problem anymore. I think the biggest threat is ingestion by eating something that has grown on polluted soil, or an animal that has eaten something that has grown on something like that. For TNT, a lot of effects. The most important ones are on the slide, and the liver can be damaged because the liver is the part of the body that decomposes the TNT. Anemia is also a very important one. So red blood cells that die are destroyed and not sufficient anymore in the body. The immune system in general, there's a very long list. Now, no one has to be afraid of TNT in the sense that the concentrations and the durations for this effect are quite high and quite long. So it's not if you have once worked with TNT in the lab that you will have a damage to your liver or anemia, of course. If we look at the possibility for getting you a cancer, in America, I didn't find a similar thing in Europe, but I didn't find exact the classification. It's a classification C, meaning that it's possibly human carcinogenic. So there's not enough evidence, but some tumors have been observed in test animals. Of course, we cannot feed a human a lot of TNT and see what happens to it. So it's always passing from test animals to humans. So C is basically nothing to worry about. And then one of the problems is that if you get it into your body, your liver breaks it down into the compounds that we already saw, the amino nitrotoluene or the D-amino nitrotoluenes, and they might be more toxic actually. But that would mean a slide for each fat. I didn't have time to go into more detail. And then these compounds, before getting you sick, usually leave the body with urine, and they are evacuated as any waste from the body. RDX, the effects are relatively different, but they require larger amounts. People have had seizures, mental confusion, and then you see an entire list of effects that have been registered, from a headache to vomiting to irritation of the skin. So it depends a little bit on one person to another, and on the concentration and the duration. So it's to avoid to ingest it, but it's almost never mortal. TNT, I forgot to say it. So there were some people, several hundred, that died of TNT in the First World War, people working in factories where munitions were filled. But once people understood how to protect themselves, the numbers were reduced to maybe 10 people that died officially of TNT contamination in the Second World War. So if you protect yourself, even in high concentrations, there's not really a risk for your health. Same classification for cancer, so it's also a classification C for RDX. And then for 2,4-DNT, well, the effects are on the slide. There's anemia, like for DNT. There's nausea, headache, for typical things when you are a little bit when your body is a little bit disturbed. Some other effects on the nervous system and on the kidneys, the liver as well. And this one is a little bit more tricky concerning the carcinogenic classification, because it's not possible human carcinogen, but it's probable one. So they put it in one class higher than the RDX and the TNT, meaning that it's probably one to avoid, because that's because of the clear evidence that was found in rats and in mice. Now, some values, and that's maybe a little bit related to the question, although the last slide will answer it more specifically. You find a lot of numbers, and I guess some people in the audience understand them better than I do. The minimum risk level, for example, that's the amount, milligram of each of these compounds per kilogram of body weight and per day that you consume without having adverse effects of this compound. So if we see that for RDX, this value is much higher than for the others, it means that it is a little bit less toxic for the body. You need to consume more of it before you get sick. So if we want to interpret that number, well, let's say an average 70 kilogram person, we multiply by this, and this is the number of milligrams per day that you can ingest orally during that time period. There's an oral MRL for intermediate, for long, and for short term. So the intermediate term is between 2 weeks and 1 year. If you stay below that limit, then probably or very probably you will not get sick of that TNT ingestion. And so this gives these values as such don't say a lot, but they give an idea of the relative toxicity of the different compounds. So TNT is the most toxic one, then DNT and RDX is relatively not so toxic. A second value is linked to the risk of having a cancer. It's the oral slope factor. And then how should we interpret it? Well, I took the example of someone says, if this is the regulation, I will give it a try. And so someone says, I have 1 year in my life, I will take this amount. If I have 70 kilogram weight, I will take this amount of TNT during every day during 1 year. And so this 0.3 actually is to be multiplied by this amount. So this is milligram per kilogram per day. This is the opposite unit. I multiply them, and then I multiply by the number of days that I have been exposed, divided by an average lifetime of 70 years. So in this concrete case, if I do this test for 1 year, I absorb this amount of TNT just for the science of it, then I increase my risk of cancer by this factor, 10 minus 7. It's relatively low. Nevertheless, I don't recommend anyone trying it, but this is the way to interpret this value. And then there's just another one, but there are tens of values. It's the drinking water unit carcinogenic risk. And so basically this should be interpreted as if I increase the amount of a certain compound by 1 microgram per liter, how much does the risk of getting a cancer increase? So if I go from 0 to 10, I have 9 times 10 minus 6, an increase in probability of having a cancer if I drink that water. That's a little bit some numerical values and how to deal with them. My last slide that I had prepared is I think an answer to the question that was in the chat. And it's basically, yes, there are regulations, and no, there are no clear regulations, because the regulations depend from one country to another, from one continent to another. I must admit that I didn't find a lot of numbers for Europe. Much of the information is from the US. And then they also make a distinction between what do you want in a residential area where people live or an industrial area where people only work. The limitations are different. This is the only European one that I found, and it was for recreational areas where people will have a lunch and will go with their children and they will play, and maybe they will play in the soil. And so we see that for RDX TNT, they didn't even give a value. But the values in this table are what the person in the chat asked. Are there some kind of a limit values that maximum that can be present in soil? Yes, but it's not so very clear which ones to use. And in Europe, it's not so very easy, even the opposite, to find values, unless I didn't look on the right place, because as I said in the beginning of this paragraph, this is not really, it's really our cup of tea, and we are usually not involved with regulations in the soil. And if we do, as the military, usually there's a law, and we are the exception to that law on specific military training sites. Now, just to, and that's more or less my final words, just to make everyone, make sure that you don't worry. We found RDX and TNT. We didn't find any DNT in the samples, but the concentrations are way below these. So I don't think we had a serious health risk in the samples that were sent to Belgium and that you collected in Ukraine. I know normally presentations ends with some conclusions, but honestly, I didn't know what to conclude here. There was much information. If anyone has any questions, shoot.
Yeah.
And otherwise, I would like to thank everyone for bearing with me this 1 hour and 40 minutes.
Okay, thank you very much, Bart, for this general section. I think indeed the idea was to not come up with a conclusion as you show so many information. So I think it's difficult, but that was the purpose of this session, to give an overview on all the different aspects related to energetic materials. Now I understand why it's not explosive, but energetic. So thank you for elucidating that. I'm looking to the audience if there are still indeed any questions left. It's good that you waited until your last slide to give an answer on the question on the levels, and maybe this will come later on as well. I don't see any questions pumping up. So I want to remind everyone so that this was indeed a general session, and you will give a session dedicated to the analytics, how to determine it in soil later on. As well, the trainees will come to Brussels, yes, in the building that you have shown on one of your first slides. Also there to do the practical session and learn how it's done in practice. So I think that's also something of interest to mention. If there is no more question, then I would like to thank you once again, Bart, for hosting this session, giving your information, and maybe also from a practical point of view, for all the people that are present. The session of this morning, as you know, we had some technical issues, but we will do it on the Monday, 4th of November. So in the morning, we had still a gap. So between your time, 11 and starting at 11 in Ukraine time on Monday, 4 November, we will have the session on radioactivity and radiochemistry in general. So I suppose Anna will inform you as well and send you an update on that. And then for the rest, I want to close the meeting and we see each other tomorrow afternoon. So there is no session in the morning, but in the afternoon related to soil remediation techniques. It will also be a general course giving you some overview of what sanitation and remediation techniques are available for soil and groundwater. So with this, I want to conclude. Thanks everyone for your attention and especially Bart for your presentation. And then we see each other tomorrow. Thank you.